case series, and today he's giving the quantum space-time seminar on that. So thank you, Sujay.
Thanks a lot, Gautam, and this great week. So this is recording of the work done with Leonora, who's here, and with my student Matsudin Raman at Chennai, and three of my collaborators, Marco, Maria Luisa, and Alberto at IMSc. This came also, most of the talk will be based on this most recent paper. I also mentioned some earlier done. So the title is S-duality triangle groups and anomalies in supersymmetric SQCD. I hope at least the terms will be clear by the time the talk is over. So this is mostly what I spoke about last week. It's a very brief summary. So we're going to study superconformal theories. In fact, the simplest of them with a single gauge group S2n and 2n fundamental vectors. And we'll always work on the Coulomb branch, where this adjoint scalar in the vector multiplet has the following expedition value. And the sort of earlier work by Simon Ingridson in the mid-90s showed us that the localized effective action, or as Shiraz and Dr. Garitani, the two-derivative duality effective action is completely specified in the following way. In terms of a single function, which is holomorphic in these AIs, and it's written in terms of the first and second derivatives of this prepotential. So f is the prepotential, and I showed last week various ways to calculate f. So given this f, then the first derivative and the second derivative completely specify the duality effective theory of the branch. So this omega is what I'll call the period matrix, because it turns out to be the same as the period matrix of a Riemann surface. And this AD is what I call the dual periods, because as I showed last week, they will relate to the period integrals on the Riemann surface. Okay, so let me go on. So the solution of these theories, which means the calculation of the prepotential, is in terms of two quantities, or two objects. The first is in this case of SQCD, is a hyperelliptic curve of this form. It's a rank n-1, genus n-1 curve of this form, and it's in terms of the curve and the differential. And the claim is that you take the curve and you calculate some A and B cycles in some places. You first do the A integrals, the A period integrals, to sort of map between what I call the A's and the fundamental parameters that appear in the curve, and then you sort of invert the relation between U and A, and then you calculate the B periods in terms of the U's, use this map to put this back in, and use the fact that, if I will go back a bit, that A is df by dA to sort of integrate in and calculate the prepotential. Okay? Let me just repeat this. So you're given this algebraic curve, and I'm just stating that this is the appropriate curve for the SUN with 2n flavors SQCD. There are some moduli of the curve that appear here. In terms of the curve and the differential, the calculation of sort of 2n periods should allow you to, or 2n minus 2 periods in this case, should allow you to calculate the prepotential. Okay. So because this is a superconformal theory, there is no sort of strong coupling scale. Instead, there is a free parameter h here. Okay, so h encodes the bare coupling constant of the gauge theory. So a slight improvement of the...
Sorry, you must have gone over all this last week, so please don't slow yourself down. But the UKs are related to the...
Coulomb. UK are the Coulomb. So it's a gauge invariant parameter.
I guess a large enough wave, they probably are literally the wave
exactly.
Inside they get more complicated. Okay, and then one which you can answer later. Of course, it's an elliptic curve. But what makes
this is actually a hyperelliptic.
What makes what's a hyperelliptic curve? I mean, why
genus 1 curve is an elliptic curve. Higher genus is.
Oh, that's what it is. Oh,
yeah. So if it's again valid in this form, is hyperelliptic.
Okay. The higher dimensional analogs are hyperelliptic.
That's the conclusion. Y goes to minus 5 is invariant.
So anything Okay, yeah. So it's just the generalization of the genus one.
Yeah, this. Okay, any questions so far? So as I discussed last week again, sorry,
is there some recovery of the Riemann surface from the period integrals that is being hinted at? So you are recovering f from ak and akd, right?
Right. Yeah.
So is there some Rayleigh theorem going on in the background, or
I don't
in
know.
some way you can recover the
curve
Riemann, the curve from the period integrals itself?
Oh, so you're saying, yeah, if I could do the integrals exactly, then I presume yes, you could, in principle, write down the curve, but typically we can't do these integrals exactly. There's some, you're only interested in some decoupling expansion near some, where the use takes some specific parameters to clear that problem. Okay, so as I discussed last week, I want to improve this solution because, like I said, it's not clear how H is related to the back coupling constants a priori. So we sort of redo the derivation of the Hamilton curve using M theory, and as I'll show in a minute, in the M theory formulation, it's possible to directly relate this parameter H, for instance, to the back coupling constant of the Gauge theory. And that's especially useful because the method being used to calculate the prepotential is not that calculating the period integrals, but instead using this localization methods of Microsoft. And as we'll see, we'll need both approaches to make sense of where we want to go. So this last bit is what you should take away from this, that a careful derivation of the curve from M theory solves this issue regarding parameter H. So let me briefly describe that. So the M theory,
what was H again, please?
so H was this free parameter. See, because these two are of the same degree, I can introduce a free parameter H.
And what is special about, let's say, H equals 0?
H equals 0 is sort of the classical limit.
And one can see that from that because that's...
Yes, because this P is your gauge polynomial. So use just know about the trace of your phi to the n, so it is by the phi. So it just knows about the Coulomb moduli. No flavors of anything. So your curve just becomes x minus a I if you wish. So it just literally says that the wave is a1 to a.
Doesn't the surface just degenerate somewhere?
Yes,
the
yes,
branch cuts
yes.
Go away.
Yes.
The y is literally p.
Yeah, the branch points
Branch points coalesce.
coincide exactly. That's the classical polynomial. So P is the classical polynomial that describes your wave. Okay, so in the M theory derivation, if you go through what I discussed last time, for the SUN theory, and just for simplicity, let's take the massless case. So if the flavor polynomials weren't massless, you would get some V minus mi here and V minus V prime here.
Sorry, I'm a bit late, but you're talking about SUN with 2NF flavors?
Yes, 2 NF, yeah.
Yeah, 2 NF, yes, thanks sir. And so the polynomial is of a particular degree.
Yeah.
Okay.
So degree n. Let's see. So SUN with 2n flavors. That's right. So there's a single gauge group. So this is the number of NS fibrates speaking, and V is the number of D4s in each interval. So it's n is the number of D4s in each interval.
So there are 2 NS fibrates.
2 NS fibrates.
2 NS fibrates, and yeah. So that gives you the degree of the
So 2 NS fibrates.
2 is the fact that it's white square.
Yeah, exactly. So I haven't related T to Y yet, but yes, T squared is a factor that you
Yeah,
exactly. So
it's 2 5, because in M theory it's one continuous fibrate.
Exactly. So I'm talking about two-way picture for you anyway. So you see Q0, which appears here in the M theory construction, is sort of the asymptotic, is a ratio of asymptotic positions of the NS fibrates, and that gets identified with the pair coupling constant of the Gauge theory. And so that appears. So we have to relate this to H somehow, as I'll show. And P is the same polynomial that appeared earlier, the Gauge polynomial that tells you the trace of the n waves. So, given the M theory curve, as I showed last week, there is a canonical differential in terms of V and P of this form. And now the same Hamilton story holds. This is the curve, that's the differential, calculate the periods, compute the prepotential. So now let's relate this curve to the earlier subgroup curve. And it's fairly simple to do that. You sort of rescale, shift, and so on, and you can directly relate this curve to this curve. And we find a precise map to H and Q. Okay, so now once we map these two curves, you might as well work with this curve, which is more sort of people are more used to such a hyperelliptic form. The A and B cycles are easily seen here. And now we can relate H to Q0 precisely.
Okay. Sujay, this curve in the earlier place where you wrote it, you had Q of 2n.
Yeah.
And here there's a very specific form.
So here the flavor polynomial is for a massless thing. So you would usually write
those are the masses for the hypermodul.
Exactly. So I would write I equals 1 to 2n of s minus 9. Now all masses are 0.
That's because in the M theory construction.
No, we can relate masses there.
Are the 6 brane.
Here they are semi-infinite D4s on each side.
Semi-infinite. So let's say we will not put them in. We just have.
We can put them in. It's easier to show the derivation in the line if we have masses here. So here all m are 0, so I just get a simple. Otherwise you can use the same.
Does this identification of H and Q0 depend on the MIs?
No. We can do the same thing, just easier to shorten show that.
Wait, sorry, what I remember is from last week was that the identification of the masses was the tough part, right?
This is not the fundamental fields. The bifundamentals were the hard.
Yes. Okay, so now you're looking at the fundamental.
Yes.
I see.
Those were easy. Because the D4s go to 3.
Yes.
Okay, so we've identified that the H parameters related to the Baire coupling constant is square. So you might ask, what is the meaning of that? Why are you interested in that? So to understand this fact, let's sort of repackage the same curve, the M theory curve, in this Pareto formulation, where we sort of what I call.
Sorry, if you don't mind, for that, I was placing out. How would you identify stage of Q0 once again, please?
So I just start with the M theory curve.
Yes.
And I sort of shift and rescale in such a way that I can write this curve in the same form.
So Q0 is just distance between the
NS factor.
Yes, okay. It's the NS factor, that's right. And I see. And then from that you identify. Good.
But earlier, Pn was a function of x and the parameter u.
Yeah, so here x is like v. Sorry.
X is like, okay.
And the UK are still there. I just haven't specified. The Coulomb model are untested this.
And you had two polynomials, right? P and Q. And the thing behind Q was H.
Exactly.
So now for H to have meaning, you have to have some scaling, something like the highest power of Q is 1 or something.
Exactly. So for the conformal case, yeah, exactly. So the real polynomials canonically.
So the highest power in X is 1. I see.
Coefficient. Okay. So if I now rewrite the curve with sort of Pareto form, which means I sort of write v as x times t, so that the differential becomes just x dt, and I sort of shift away the next leading order piece here, so that the sum starts from 2. This is what is called the Pareto form of the curve. Then the sort of the Baire coupling constant becomes sort of the location of the puncture, this puncture Riemann surface which I have used in the class. Okay, and I do it in this way because this is something that he already did in 2009, where he identified how S-duality acts in these superconformal series. Okay, so in these xt variables, this is how S-duality acts, and it effectively takes the coupling constant to 1 by Q0. So this is why I wanted to rewrite H in terms of Q0, because in terms of Q0, the action of S-duality has been understood already. Okay, so it's an important map to it. Yeah.
This is just one there, right? So this is a punctured Riemann sphere.
Sphere, yes.
Okay.
Sphere.
Right.
Yes.
So the roots of that polynomial are the punctures.
Punctures.
Okay.
But Sujay, I was not going to ask, but if you can just go back. Yeah, I'm just. So geometrically, you might have thought that the H coupling, which is related to the size of the D4 grain,
the positions, the relative positions of the NS factors.
of the NS5, but I'm saying if you finally do reduce to a 3 plus 1D gauge theory, that gauge theory in 2A comes from the D4 brane theory. And
the size of the extra direction.
It's the size of the extra direction, which is of course related to the separation between the edges, right? Now, if you look at this expression, for small q0, h is going like q0, right?
Exactly.
But for large separation, it goes like 1 over q. What's 1 over q0? What's the geometrical reason for that?
You mean so the geometry is best understood by looking at from the M theory foundation vector. This is just a traditional way to write this subinterval curve for SQCD. That's all.
It's just that H is not particularly useful.
Exactly. It is not.
But I mean, it should. If I was a dumb physicist, I would do the dimensional reduction on the D4 brane to get the gauge coupling, right?
Yes, exactly.
Now,
that's what we didn't get. So it's not.
Yeah, well, I mean, we're all.
That's a standard.
So why is it that, I mean, geometrically, why is it that if the separation is increasing, the gauge coupling is no longer scaling with the separation? Why is that?
The separation is Q0, not H.
Exactly.
Q0 is Q0.
H is some stupid thing you put in your equation, and then you figure out what the separation is, and that's Q0. And that's it.
But H, no, but you are going to integrate H as.
I will interpret at the end.
Okay.
It's very interesting.
All right. So that is meaningless. So that is
another. The moment is meaningless.
Okay,
that's
another. Okay, good. So this is another reason to see why Q0 is the guy transforming nicely, is it?
Yes.
Okay, because
but we'll come to exactly what H is at the end.
I'm with you because Q0 geometrically should also be the coupling.
Yes.
It's the separation.
Q0 is the ratio.
Yes. Okay, I'm with you. Thank you.
Okay, so we've understood how S-duality acts on Q0, and now let's look at this function H, and we see that H is left in. Sorry.
Okay, just go back to that. How was that?
Yeah, just an inversion and T, so Q0. So you see that H is left invariant under Q0 is 1 by Q0. Okay? That's an interesting observation. And this is related to something that was already conducted a long time ago in the mid-90s when only this kind of curve was available. Okay? Angelis and Buchel had suggested that monotonies in this H plane around the singularity 0, 1 infinity generate the S-duality group of the theorem. Okay, and let's try to understand how they came up with that. So we
let me understand this. What is monotomies in the H plane and generate the S-duality?
So you can see that the curve degenerates whenever H is 0, 1. You can check.
Okay.
So there are singularities in this H plane now, and they claim that let H go to e to pi H. Okay, and you see. Yeah, that explains. Okay, so now I think that's a direction.
Just one more thing.
Yeah.
What's the S-duality group?
That's a good question. So for the simplest case of SU2 when M is 2, it's just the SL2 set of group. For higher rank theories, it's more complicated. I'll have to explain. But for our purposes, we'll mostly use just this Z2 inversion, the S transformation of this.
That's one of the generators.
That's one of the generators, but that's not the planet was.
Wait, just Q goes to 1 by Q leave that invariant, that H invariant?
Exactly.
Now I understand the monotomy. Sorry, thank you.
I'm saying this observation is consistent with an earlier proposal to Angelis and Buchel that monotomy is the S. Okay, so now let's try to explain what we do.
So we take this H representation is just parameterizing the different curves, whereas Q gives the different duality frames.
If you wish, yes. Perfect. Okay, what we do is we take SC1 with 2 flavours, and we calculate using equivariant localization the prepotential, the dual periods, and the pictorial matrix. Okay, as a power series expansion.
This so the S-duality group can one think of that as say the fundamental group of the modularized space of.
You should, yes.
H thinking of
you should
think of it
exactly.
as a modular.
Yes. In this example, yes. In this particular model. Okay, now what I'll do is using the Angelis Buchel definition of the S-duality group, I'll embed this S-duality group in the traditional electric magnetic duality group that I discussed last week. And that obviously acts on the periods and the dual periods as a symplectic group. But sort of inequivalently, Gavito's work tells us that Q0 is inverted under this S transformation. then what we'll do is to use these two sort of seemingly disparate pictures to completely resum the instanton expansion.
If this was not known before, that Q0 goes to 1 by Q0 under duality?
This paper sort of clarified, this for all curves. I think we've been looking at it for several examples. So for this,
but for this particular example,
it was known. I think it was known what he just said. That is,
yes.
Yeah, I think it was known. So what we use to put together these two different points of view. So this localization gives you sort of a power series for weak coupling, and this S-duality gives you some non-perturbative input. We put these two together to sort of give, to completely resum the instanton expansion, which means that we'll be able to give modular expressions for the periods and the dual periods.
And localization is not powerful enough to give you the full answer.
No, the localization gives you, as a power series. 1 instanton, 2 instanton, 2 instanton.
So it gives you every term, but then you have to sum it.
You have to sum it, yeah. Yeah. Maybe it is.
I don't know much about it, I'm just asking.
Yeah, I think as far as I'm concerned, it's a tool to give you sort of a VP coupling expansion. Again, what we find is the following: that even in the massless theory, the pair coupling gets renormalized. I'll show exactly what this means. What we find is sort of a non-perturbative formula between the pair renormalized coupling constant in terms of something called J invariance of a particular triangle.
And group is the thing that generates by the 3 monodramas.
Yes.
And renormalized coupling means coupling of the U1 theory?
Of the
effective
U1, exactly. So I'll try to show this in detail. And then we'll see that the action of so what is this triangle group? So this action of the triangle group is completely sort of fixed by this Q0 go to 1 by Q0 relation of Kyoto and this renormalization. So this one gives you a power series, and this Q0 go to 1 by Q0 of Kyoto gives you some non-perturbative constraint, and the S-duality constraints are sort of solved by this particular formula. And we'll be able to sort of derive this as Buchel claim in great detail. So that's the story in the massless case, and the masses turned down. Something very similar happens. So the modular structure is maintained, and we'll be able to resum the sort of mass corrections to the prepotential in terms of modular forms.
When you say masses, you're turning on masses for both the fundamentals as well as the bifundamentals.
There are no bifundamentals. That's all. So it's
because it's one group. Yes, thank you. Yes.
Now we're asking to try next. Yeah, that's what we're trying to do. Okay.
Okay,
this is what we find.
Can't you have, I've forgotten, you can have these 6 brains or something in 2-layer picture, no?
Yes. But here I just have 2 NS5 brains.
Okay.
So there's just one gauge group.
This is one gauge group, but you could add extra, I forget about this.
You can add this brain, but it's much more useful in that mode. So here I just have 2 NS5 brains, D4s, and then semi-nuclear D4 that extend on the side. So it's just one.
So if you introduce these MI terms,
yeah,
then it's a general hyperdelectric surface, so the modularized space for that is pretty big, right? So
yeah, but
would you have more than a triangle group and this?
we'll see.
Okay.
We'll see. It's sort of a constructive thing, so we'll see. Okay, so the caveat to all this is that we work in a very special locus of the Coulomb branch. Okay, so for SE1 theory, there are A1 to A-1 independent Coulomb moduli. But we set most of them to 0. Okay, and we work in a ZN symmetric locus. Okay, so in particular, the Hamilton curve also has this ZN symmetry. As you can see, only actually the N entry.
So UK is 0 for all, only
the highest Casimir.
Highest Casimir is turned on.
So, yeah.
What does that mean for the eigenvalues?
I'll tell you in a minute. So here, so this is also the curve that Argyris Buchel took in their mid-90s paper, and they just calculated the discriminant of this curve, so where the curve degenerates, and they noticed that exactly for h equals 0, 1, infinity, independent of the value of un, no matter where you are on the special locus, the curve degenerates. So that gave them an idea that this is a sort of an invariant definition of the S-duality group. So they
are they the nth roots of unity?
Yes.
Okay.
They will be in the next one.
Yes.
Okay. So since the curve degenerates, no matter what value un is, so it's sort of it doesn't care where you are in the moduli space. So those monotomies they proposed generate the S-duality. So it's something intrinsic to the theory, independent of where you are in the moduli space. So specifically, what that means is you just take, just solve this curve. In the sense, you find the roots of the curve, find the locations of the zeros, right? And the cycles have a natural symplectic action on them. So you just follow the roots, as I say here, as h goes to the 2 pi I h, and you'll see that around h equals 0, 1 infinity, you get these, each A, B, C, D are n minus 1 blocks. So you get a symplectic matrix that act naturally on these periods by periods multipliers. So what I'm saying is that you have natural action of S-duality on the period integrals of the curve. Okay? So explicitly you can find that if C is the Cartan matrix of SUN, that's the T action, and the S action is in terms of some given n minus 1 by n minus 1 matrix P. If form is an important, this story that's completely explicit. The action of S-duality on the periods.
SP 2n minus 2 comma z is exactly the mapping class group of the Riemann surface of genus n.
No. It's just the group we discussed last time, the electric magnetic duality.
So they're rotating the.
It's a change of basis. It's a basis of one cycle you have to choose. Right? So
this maps onto
exactly.
the symplectic.
So you just embed in the group each of these.
When Gautam starts saying mapping class group, I feel very inadequate.
Let's move on.
Sorry, you might get to this, but so you've basically chosen a point in your moduli space where the center of the group is unbroken, right? I mean, the Z and symmetry is unbroken. And I'm just trying to understand, you have whatever n or n minus 1 U1s. You could try to define a S-duality group for each of them. That is, each of them has a gauge coupling. And say that I take it to minus 1 over itself.
No, that's not what I'm doing. We'll see more about it, exactly.
But there's some action for each of the gauge couplings that...
right, exactly. So
and that you're going
n
to...
minus 1 matrix is exactly that.
It's not that each coupling goes to one by itself, is it?
No, so this omega is the p-period matrix that tells you how the U1s are coupled. And on omega, it acts like that. So it just rotates it. It just chooses different bases of one cycles and everything changes accordingly.
Yeah, but the couplings are the period matrix, right?
That's exactly which is omega. If I go on, I promise to make it clear.
No, please.
Sorry to interject. So finally, you're going to be taking something like the upper half space.
Yes.
Portioning out the symplectic group.
Yeah.
And on that, you're going to be acting on the symmetries given by.
You should, but because we are in the special vacuum, we will see what happens. Omega is a very special form, as I said.
Yeah, that's what I was thinking.
So ideally, you should have some higher genus theta functions and so on, right? But in the special locus, something very special happens. That's what's special.
And the speciality comes from the fact that all the MIs are 0 or.
At this point, no, we can turn MI. So this Z and symmetry is important. There's a Z and symmetry there.
So that's this U1. What Shiraz was saying. There's a nth root of unity.
Exactly. Yeah. Exactly. So let me please go on there. Good. So in the special vacuum, there is only one independent pair of A and A units. Okay. So all the A's are just nth roots of unity. This is one overall scale, and you can check that the dual periods, and this is unchanged by quantum corrections. Again, the development in terms of just the n minus 1 conferences. Okay, it's very big. You just chose these to be independent. So there's only one pair effectively. Okay, and the result of the next analysis, I'll tell you the details, looks like this. So the dual period, if I take, so this is the classical result. Okay, Cn is some function of omega, as I'll tell you in a second. There is some one loop result, constant number, and there is an infinite series of instanton. And even with the massless theory, okay, such a sort of renormalization happens. So with this tau is what we call as an effective coupling constant. Okay. And this is unlike what happens, for instance, in the n equals 2 star theories, where there is no renormalization. The classical one tau naught in the massless theory is the quantum tau naught. Okay. So it's a slightly strange result.
So you mean this is true for this is true for the SUN case, but not the what do you mean?
So this is SUN with 2n fundamental flavors. And I'm saying here this is SUN with a joint.
Okay, that's it.
Okay, so now we take this relation. So this is the full quantum result, and let's act with S-duality on the periods. We know exactly how they act because we derived the symplectic matrices that enforce S-duality, or this S action, so to speak. And this is how it acts. So, as predicted, as expected, A and A dual get exchanged after some phase factors of n roots of unity. So, let's impose consistency between this S action and the result that we got, the fully quantum corrected result that we got. And we find that this necessarily means tau must transform like this. Okay, where alpha takes this form. Okay, so see what I've done. I just calculated this. This is actual calculation, and this is S action from the EM duality. I mean, S action is embedded in the EM duality. Just impose consistency of these, and I'm forced to transform tau this way. Okay, and we get this sine squared pi by n, and for n equals 2, 3, 4, and 6, these are integers. So they're very special, and these we will call arithmetic couplings. And so the discussion of the SU2, SU3, SU4, SU6 cases will be different from the other cases, as we see.
Wait, sorry, this S of tau is just a transformation of the low energy effective parameters when you go around, right?
Exactly.
Now, I thought that had to take a particular form, this SP whatever.
I'll come to this.
Is that consistent with this?
Yes, it is consistent. So what we'll see is that, so the question is, how does it act on the P-in matrix? Right?
Sorry, how is tau related to the gauge couplings of the...
I'll come to this. That's the next one. So how does it act on the P-in matrix?
So you picked out one particular
That's
A
one.
and
I didn't pick it out. The latest of calculation picks out one.
Oh, but you had n minus one of them. So
Of what? A.
of the A and ADs.
They're all proportional.
The symmetry,
They're symmetry. So you see, the A and ADs are all proportional to a single pair. A and
Oh,
A.
they are all proportional. Nice.
So you can pick any one. I just pick one.
So in this particular case, you have very simple curve, right?
Yes. Because it's a Zian symmetric curve.
Yes.
Okay, so now what happens to the P-in matrix, and what is this tau that it is here? So at the classical level, it's of course tau naught times C, where C is the Coulomb matrix of SU1. It's a diagonal result. The one loop result was already known to Pinahan and Chansky in 96.
Sorry, what is C?
C is the Coulomb matrix of SU1.
Classical level tau.
You can just check this. You can just take half tau x squared and so on. So here at the one loop level, they found sort of roughly n by 2 distinct.
I'm sorry, just to keep it trouble. Which singularity are you going around?
Where?
This omega is what? Is the
No, omega is d squared f by dI, dAI, dAj.
oh.
It's a matrix, yeah.
So okay.
Yeah. So at the particular level, you find people found roughly n by 2
That's just
distinct
coupling
matrix
cost.
structures.
That's just the coupling cost.
The U1 to the n minus 1 coupling.
Yes, it's right.
So they found roughly n by 2 distinct matrix structures, which I denote NK.
Just to say this.
You never get to the end.
It's better we understand how
Exactly. It's best to uncover a little than cover a lot.
The different humans, of course, mix with each other, right?
Yes.
That's partly why it's a matrix.
Exactly.
Sorry.
So the external corrections, they do not change the matrix structure. So what you find at the perturbative level continues to hold even with external correction. This is just an observation. You do the calculation and you find that change. So instead of this, you get some sigma times n. Right? There's some expansion instead of n by 2. See, you should have expected n times n minus 1 by 2 matrix structures. But instead, in this special locus, you will find n by 2 different matrix structures. So Zian symmetry cuts out everything else. And if you have less than omega, it's a disaster. Sigma goes to some horrible rational function of the other sigmas, or
And NK again is some matrix structure.
Yeah, I haven't specified it, but you can do it. But what to observe is that it's always possible to form combinations that diagonalize the S action. What I mean to say is the following.
Wait, sir, you first said that instead of corrections do not change the matrix structure.
Yes. The same as the one loop.
One loop.
So let's take SE4 for an example. And what we showed was that there are...
But it changes the coefficients. So you're saying it's the same basis.
Exactly. Same basis. So what you find is that you can always write it in this form. So SE4 there are two matrix structures. and the coefficients, now I call taus instead of sigmas because tau is will diagonalize this action. And they have this expansion. So it starts with classical piece, it starts with some constant, 1 instanton, 2 instanton, some rational numbers on this. Now if we do the S transformation with this basis, which means the M are a very particular form that I've chosen, and you see this happens. M's are left invariant, and taus get inverted. Okay? And one of the taus will always invert with this guy, with k equals 1. So that's the guy that appeared in the A dual. So there are n by 2 different matrix structures that appears in the K matrix, out of which one is always chosen. One always appears in the expression for the dual periods. So A dual is always some Cn times A times tau 1. It's always tau 1. Okay?
It will normally aim something.
It's a calculation. So the one loop analysis gives you the result. And the high incident correction, you can show it in all writing down. It's a sort of constructive proof. So it's not a proof, but in every case we have checked this is the observation. Okay, so this is how we claim S-duality acts if we believe this story about embedding the S-duality in the symplectic group, therefore knowing how S acts on A dual and omega, and just acting as an omega. So how is this consistent with, so Q0 appears here in this fashion. How is it consistent with Q0 versus 1 by Q0? Now we see, given this, each of this is an independent function of Q0.
So you've been talking so far about the one element of S-duality which was Q0 versus
yes,
1 by Q.
That's all I talk about for now.
But there are also the theta, the shifts and
the shifts don't change Q0.
Yeah, exactly.
They don't change Q0. Only for the SU2 case something notable happens, but I will study that. You see, now we can independently invert Q0 between Q1 and Q2, where each of these are e to the 2 pi I tau 1, e to the 2 pi I tau 2. Okay? And if you just plug these numbers into the online encyclopedia of integer sequences, you'll find, at least in some cases, ratios and beta functions. Okay? That's perfect because now, if I use what I know from the basis analysis, this symplectic group analysis, that exactly implements Q0's 1 by Q0. So we trust this as the sort of non-perturbative completion of this map. So Microsoft just gives you the first few terms, Dialto gives you this, together they give me this sort of non-perturbative exact map between mere coupling and each of the terms.
So this is a conjecture that Q0 is this, and that conjecture is consistent with this.
Yes, it is. Okay?
And importantly, for the different taus, you get the same Q0.
Yeah, so see, Microsoft only gives you Q0, nothing else. If you just take the raw data, it's some equivalent expansion of this. So we have to repackage it in a form in which S-duality is manifesting this. I'm nowhere near the end. Is it okay? Can I just
keep going?
And this works for almost all the arithmetic cases. Okay, so for each case, so by SU2 and SU3 is 1 coupling, SU4 there are 2, SU6 there are 3. And for all of these, except one, where alpha is 1, for every other case, I can write Q0 in this nice form. And each tau k transforms like minus 1 by alpha k tau k, where alpha k takes this nice form, sin squared k pi by a.
Just to understand, tau is the physical gauge coupling.
No, tau are those coefficients of those matrix structures that appear in the Lorentz interaction.
So in terms of them, then you would calculate.
Exactly. And for each of these, and for this jet form, I can check that when tau goes to this, Q0 goes to this. Okay, what's wrong with the one guy? So you can ask this, highly unsatisfactory is one guy that's sticking out.
Oh, sorry, what was this one guy?
So when alpha, so there's one coupling in SU6, the tau 1 has alpha equals 1. So 4 sine squared pi by 6 will be 1, and I can't use this one. Doesn't make sense. Okay. So that one has this is the expansion for that. So there's no ether quotient expansion for this. So the question is, can you find a more inclusive formula? And the answer is yes, of course. And the answer is in terms of J functions. Okay, and we sort of, so this you can just check. So take the usual J function of SL2Z, do a B coupling expansion, and compare this with what we have here, and they match after the first, whatever, 2 or 3 terms. Okay? So this 1728 is sort of J evaluated at I, which is the fixed point of the S action. Okay?
So just to understand, you have this expansion, different matrix structures,
yes.
And somehow the first matrix, N1, its coefficient, alpha 1, is different from the other.
In the sense that it appears in the expansion for the A dual as well. Right? So let me write this down here.
But I mean, was that choice?
So, no, it's not choice. It's just that one of them, so K equals 1 to whatever, and by 2.
Is this what is separating?
No, it's the behavior of S. So you see tau 1, so tau K behaves like alpha K tau K, where alpha K is 4 sine squared K by 1. Okay. So K is 1 for the tau 1 guy. And if you calculate A dual is A times tau 1 times some constants. Okay. And tau 1 is fixed separately by the transformation of A dual and A. So it sort of selects the S action, the periods will select which tau it takes. This turns out to be K. Okay, so this seems like a very nice formula. The question is, can we write the others in this form? So we had an eta quotient formula here.
So this reproduces Q expansion is also consistent with S2. This form?
I will come to the S action in just a second. Okay. First, let's just try to mask the fact. So, what we will do now is to revisit the mathematical structure of this S action for the other cases when alpha K is either 1, either 2, 3, or 4. So, in those cases, it turns out, only for those cases, the S-duality group has a subgroup which is also a subgroup of the modular. Okay, and that's generated by T and S prime. So, only for the arithmetic cases, you can form T and S prime that generate a gamma 1 alpha K that is also a subgroup of the full modular. Okay? But
So it's the congruence group for
yes, number 1, yes. And but of course, this is not the full S-duality group. The S-duality group is this, along with this S transformation, which generates this the thing that we saw, minus 1 by alpha K. Okay, so we need to. So really for the arithmetic cases, we can think not in terms of this is S action, but in terms of this gamma 1 alpha K, sort of adjoined with this involution.
Actually, Sujay, you're losing me. What question are you trying to answer here?
Can I write the eta quotients in terms of the sort of same form as the J? And the answer is yes, because this group was studied by Xavier, and helpfully in his paper, he has given J invariants for this gamma 1 star. Okay, so these groups also have hauptmoduls. It means modular functions of modular invariant functions under this group gamma star can only be written as rational functions of some J function, and he lists the J functions for each of these groups. I can see the same kind of eta appear here.
Sorry, I'm revealing the ignorance here, but the usual J function is invariant under
SL2Z,
right?
So this will be invariant under the gamma 1 alpha.
Gamma or alpha star, right? Okay, got it.
And we can also evaluate J at the fixed point of the S action.
and this is an exhaustive list of J functions that they return to the congruence.
For these cases, of course, yeah, but there are other cases in the list. There are other n values that they list, but which don't appear in the physics context. So now I just take the J functions, take the D values, plug it in, and I get the same thing. I get the eta quotient. Okay?
So it's a uniform formula.
Uniform formula, at least at the moment for the arithmetic cases.
Yeah.
For SU2, SU3, SU4, SU6, when alpha K was an integer. For those cases, for now, we have a J function. And you see, from this formula, it gives you a very natural geometric definition of what is S-duality. You just go around the fixed points of the corresponding S, T, and ST inverse action. And this formula goes will give you Q0 goes to 1 by Q0, or Q0 goes to Q0. Okay? So, this should sound like this is what we started off with. We said there was some H-plane, okay, in which I went around singularities at 0, 1, infinity, and that generated my S-duality group. Now I come back to the same story. There is a J-plane. Okay, now the singularities are located at 0, infinity, and 1 by B. And let's check that the monotomies in the J-plane. Yeah.
I mean, now you're looking at the congruence group, right? So gamma naught alpha K or something.
Yes.
Gamma naught
Star. So this is adjoining with this Hecke evolution that I have.
Yeah.
Yeah.
Right. But once you pass to a congruence group, you're going to have more cusps, right? So you already had 4 J functions. So how is it generated?
No, 4 J functions in the different cases. Each of them only has 1 J function.
Oh, I see.
Yeah. So see here, this is the alpha value. Alpha is 1, alpha 2, alpha is equal to 1, alpha 2, alpha 3, alpha 4.
Yeah. So what I can't get my head around is that because you're looking at generators for the congruence group rather than SL to Z, there should be more than 3 generators.
3 generators of. Oh, I see.
Of the S group, yeah.
You're saying there should be more similarities in the J-plane, is it?
Yeah.
Okay. I don't. Here I'm sort of not. My depth of knowledge in this is not existent. But yeah, maybe that's one. So the basic point is that we have sort of geometrized the Coulomb inversion and the T action as monotomies in the J-plane. Now let's make contact with what we had earlier, which is the S-plane monotomies. And if you compare the two, so you see we earlier had a Q0, H was a function of Q0, some Q0 1 plus Q0 whole square. And now we have a Q0 versus J map. If you compose the two, you'll find that H plane is just the J map. So we give an interpretation of this H parameter as this J invariant of some group gamma star, such that monotonies around the singularities around infinity, or in this either in the J language 0 infinity and 1 by B, generate the echelon.
That's sum over K there?
No. Independent of K. That's fine. So there is a universal formula independent of which tau you choose to parameterize them.
Actually, just like the was. Actually.
Yeah, just because he got the same Q0 for different.
Exactly.
So is this like saying that the running of the individual E1s is such that whenever it's becoming non-abelian in the modular space, it's just they are all agreeing.
With the unique coupling, yeah, that's what we're saying. Yeah. Of course, it's not running here because it's a superconformal series. Yeah. These are sort of finite
okay, as a function of the modular.
Yes. Yeah, I'm not really sure about that, but yeah, there's an agreement between what we call the Bayer coupling constant and its taus. There's some compatibility.
To get equation 53, you do H in terms of Q0,
yes,
and then you do Q0 in terms of J, which is just compound.
Composition.
Yes.
Okay. Yes, what she's going to show you that there's a sort of universal behavior of J, irrespective of which tau you choose to write in terms of. Because for the sequel there were 2 taus, whereas you see there were 3 of them. It doesn't matter which one you choose. As tau approaches the cusps, H behaves the same way. J behaves the same way. And this is one of the improvements of our work on early literature, where they choose the one or the other. It wasn't clear why they should choose one, but here you see that they were all right. Just that there was a more global picture. And the most interesting thing about this is that the J invariant has known expansions near all the cusps. So in principle, you can ask strong coupling questions. We haven't asked any yet, but in principle, one should be able to ask some strong coupling questions.
Why arithmetic? Why are you? Is it just for computational comfort?
This is the first half. The second half, we will definitely do it. Actually, maybe right now. Okay, so the arithmetic cases are under control. The modular structure is really seen with the period matrix, and it is written in terms of these taus, which are quantum corrected.
So just to make sure I'm understanding, it was important for this that the genuine S-duality group of the UV theory could be embedded in the S3 whatever group.
But in some sense, we didn't have to assume that. We sort of derived that by this formula, Q's universal. So we couldn't have come to that without sort of having that intuition in the back of our mind, but yes.
I missed something. What was the arithmetic nature of this?
Whenever these are integers, tau goes to minus 1 by integer times tau.
And the 4 is very important for them.
Yes. Okay, so what do we say about the non-inverted cases? That's a natural question. And we are still in the master's limit. Hopefully we'll be able to run a master's at some point. So let's take SE5. Okay. Let me just give you the raw data. If you just do the localization, then you'll find all these strings.
It will be arithmetic over some number field. It's not over Z.
Effectively,
or Z root 5 or something.
We'll see. Yes. So tau 1 and tau 2 are such that so again I have diagonalized S action. So these are written in such a way that when I act at S on omega, each tau goes to minus 1 by alpha k, but now alpha k is again of the same form. But these are invisible. There are some real numbers. So in principle, if you go by earlier methods, you have to invert this, and it's a disaster. You're going to get a mess.
Sorry, this is stupid. I thought you said there were n minus 1 different terms.
N by 2. So yeah. So again, the question is whether we expect any sort of J invariance to appear. And it's very convenient that Professor Oosterley was visiting us from Paris, and we asked him whether he knows these groups, and he said it's too bad it's sine and not cos, because if it's cos, it's a Hecke group. Okay? So let's see what that means. So a Hecke group is defined as follows: SL2R, where S square is 1 and SC to the P is 1, but P is an integer. And you can equivalently phrase that as an action on the tau, where tau is shifted by 2 cos pi by P. If you just change some variables by the scale factor, you'll see that whenever alpha takes the form 4 cos squared pi by P, okay, it's a Hecke group. And for arithmetic cases, we can write every sine squared what we had in terms of cos squared. So all those cases, so those gamma stars are nothing but Hecke groups in this case. Okay. For non-arithmetic cases, also we can do this, but P is rational. Okay, P is rational with some x by n. Okay, how does this help? Well, the point is that for Hecke groups, there's a recent paper by Charles Doran et al., in which they calculate, they show you how to get sort of expansions of these hauptmodules or these J invariants near cusps. Because they satisfy some third order differential equation that depends on coefficient when on this P of the Hecke group. And you just use the appropriate ansatz near the whichever cusp you're interested in, solve this equation, and you have your expansion for your J invariant. Okay? So this is the analog of the usual J equals 1 by Q plus blah blah blah. And again, there's a nice formula in the paper for J evaluated at various fixed points of the S action or T action, whatever it is. So now it seems like a godsend. We have a Q0 formula in terms of J invariance. There's an independent way to get the J for every Hecke group. So we'll just try. Put the formula for the J invariant into the Q0 formula and see what happens. And if you calculate this D function that they have, it's exactly the one loop answer that we had from SQCD yesterday. And it works whether P is integer or not. So this is a mystery for us. We have a whole formalism that works whether P is an integer. Okay, groups. But we just put the rational value that we had, right? And it still works. The same formula that they had sort of continued to rational values. We get the same necklace of expansion, the localization expansion, from our master formula, Q0 versus G. And we checked it to up to SE15, just to make sure we haven't made a mistake. Okay, so the claim is that there's some, at least in this special locus, there is this J invariant that appears, which is a J invariant of some Hecke group suitably continued from P integer to P rational values. That seems to know about the instanton localization expansion of layers. And they're related by this formula, Q0 versus J. Okay? So we just summarize what we have so far. So in the massless limit and in a special locus, the period matrix can be written like that. Okay, K goes from 1 to n by 2, like I said roughly. The S action on Q is obtained by this symplectic group we had by embedding it in the EM duality group. And they leave the m's in between, and tau is transformed like so, where alpha is some sine square k by n. And the dual period picks out just tau 1. The S-duality group acts as a sort of generalized Hecke group on each of the couplings tau k independently. On each of these taus, S acts like so. And the bare coupling of the gauge theory is related to the these renormalized tau couplings by this master formula. And we sort of geometrized the action of the S-duality group by relating them to monodromies in a J group. And the Summerton curve has a uniform behavior in the cusps independent of which tau you choose. There's a nice compatibility. Okay? Alright, this is end of part 1. If I can go on, I'm going to. Okay. Mass definitions. So now earlier I had taken x to the 2n. Now I should put this polynomial. But if you put a generic mass polynomial, you will break the Zn. Because you want to remain in the locus of special vacuum where Zn is preserved. So you're only allowed to turn on 2 mass parameters. Instead of this Casimirs, there's 2 independent mass parameters that are available to us that maintains this Zn structure. Now it depends on x to the n and not low parts.
So you're putting in this set mod and symmetry by hand.
By hand. I'm restricting myself to a special locus where this is visible. Okay, I hope this is clear. So I'm already turning on 2 of the available 2n Casimirs.
I don't understand. What is the product over I there? It is.
No, it's not there.
It's not there. No,
It's not there.
yeah.
No, sorry. Originally it was like that.
Yeah, but
sorry.
then you just yeah.
Okay. Good.
So I was I'm not understanding why. So the original z to the n was inside the gauge group. Right? Was some subgroup of the gauge group.
Yeah.
Now you're adding flavors,
Yeah.
all of which have just transformed as fundamentals in the gauge group. Why do you need to restrict? Why is preserving this permutation symmetry inside the gauge group?
Well, I really need a Zn invariant symmetry curve.
I see.
So it really should act at the level of the cycles of it.
Yeah. I'm just wondering if there's some sort of color flavor going on. Because naively you might think that the flavor
should be independent
of the color.
So the Zn started off by as a sort of action on the adjoint wave.
The color, basically. Yeah. And now somehow you're restricting the masses for the flavors.
But I think that conformal symmetry will always demand that you have 2n, so that the color is already.
No, the numbers will but why are the masses constrained? Okay, good, please.
Okay. So I'm just going to give you what the result looks like. So if I do the Hecke analysis again, this was my master's answer. And now I have some polynomials in these mass parameters. And with some, for each coefficient, I'll have some Q0 expansion. So this is the form it takes for any SC. And now I again impose S-duality on the periods on A, AD, and A, leaving the T's invariant for now. They're not acting on T's.
So the equation 73 comes from where? This is from the M theory or from?
No, it comes from the Nekrasov calculation.
Yes.
In the special one. So now to see what kind of objects Gn are, I just again act with S on AD and AQ and I find the following. If I form this combination X, then Sx scales like that on S-duality. Now I act with S on the right hand side of this X and you find this equality. See, now instead of A dual appears. I have to act with S on everything. Is this clear?
No, actually not really. Sorry, this S is the UVS that you're talking about?
No, this is the action on A and A dual. I mean the symplectic transfer.
Symplectic, yes.
So you just know how to act on A and A dual.
Yes.
You just apply the rules and see what you get.
Okay.
And you find that this quantity X by this, when X is this summation, is the same as this. But now instead of A dual it is. So that I'm acting with S-duality on it. Okay. Now I have to put back this expansion here as a power series in 1 by A and just compare terms order by order. Okay. It's a simple power series comparison. Coulomb.
So GM is some polynomial or something?
It's a polynomial in the mass Casimirs, and it's a series expansion in the Q0. So for a given flavor polynomial, I have some Q0 expansion.
And then there you're supposed to evaluate S for that value of GM using 75? Is that
Using, so you substitute for AD from the first equation here.
for AD? And S of GM is given by...
Is unknown. We are trying to determine what S of GM is.
Ah,
So S of GM will be written in terms of GMs. Okay.
okay. And then what is the... I'm still confused. I mean, how do you get line 76?
It's just S on the RHS. S of GM is exactly that, and S of A is known.
Oh,
It's like
okay.
omega times AD1.
I see. Yes, okay.
So as a series expansion, we find the first term, the leading term of the series gives me this. S on G0 is some power of tau times G0. And if I do the S prime transformation for the arithmetic basis, so from here on I'm going to calculate arithmetic basis. I'll get sort of C tau plus D, so to speak, tau time, it is a power times G0. And we conclude that G0 is a modular form of gamma 1 alpha 1 that has well-defined transformation under S, which is not part of SL2Z. Okay, S was outside SL2Z, if you remember.
So the two masses, M and M tilde, are inside this
Are built into
G0.
G, exactly. So this applies to each coefficient of the mass Casimirs. Exactly. Okay, so what about the higher cases? Higher cases we find.
Sorry, Sujay, I'm sorry for being so stupid, but what do you mean by X was not inside SL2Z? Is that?
So no, it's SL2Z. Exactly. So for the n equals 2, 3, 4, 6, okay. And we had this gamma 1 alpha k subgroup of SL group. So the S-duality group.
This is the UV S-duality.
No, this is again acting on the towers.
What do you mean by S-duality? Sorry, it's just one of these.
It's the symplectic matrices, the S transformations that, but they act when they act on tau, they just act like tau goes to minus 1 by.
There's a particular symplectic matrix that has this structure.
Exactly.
Okay, fine.
So it has a subgroup gamma 1 alpha k that is also a subgroup of SL2Z. But whenever alpha is is one of these things, the alpha transformation itself is generated by something that looks like this, and this is not part of SL2Z because it's not an integer. Okay, so this S parity is just the sign that appears here. And the first step towards the next, what we have to do next is to just tabulate gamma 1, 2, 3, 4, all modular forms.
You had mentioned something about SL2Q.
No, I didn't. No.
In discrete subgroup, which is not.
Oh, when P was on rational, yeah. No, those don't play a role. So I'm just coming, I will not discuss non-analytics. That we don't understand.
So just let me completely understand.
Yes.
This S was one of your SP whatever elements, right?
Yes. But now you see how does it act on the individual tau k's.
Okay.
It was a matrix, and the individual tau k action is just an inversion like this.
Okay.
And I represent that as a matrix. So this should be thought of acting on tau k by itself.
Yes. And then if it's not part of your SL2Z,
Yeah.
but it is a duality of, I mean, it is.
Of course, but I can't use modular properties. The modular properties are related to modulus to subgroups of SL2Z. So you see, S acting on G will be some root alpha tau. So it's not part of the model.
Okay.
So what you do is to classify all modular forms of the various congruence subgroups you're interested in. In addition, check how they behave under S.
I see. So you need that to be a solution.
Exactly, and as an extra consideration, it's great because it halves everything by your basis elements by half. Okay, so G0 is a modular form of gamma alpha 1 with some specific S parity. Just listen. Okay. So for n greater than 0,
It's always going to be quadratic integer, right? I mean, it's going to be z square root n for some
yes.
prime or so some integer n, right? But it's always going to be like this.
No, if I have 4
Even
times
though
by 15, is that
Oh.
it's not anything? It's a problem.
Yeah, okay. Never mind. Okay.
This back to a S not being in your SL, whatever, has nothing to do with the mass center.
No.
So that we should have encountered in part 1?
Yeah, that
and we did
part 1. But then,
how much time is
I'm sorry.
Sorry, one second. So when alpha k was something like 2, 3 or 4,
yes,
even that you identified to be part of the usual SL2Z, is it right?
we had a gamma 1 alpha, so we see, so let me start this.
So for alpha k equal to 1, you found that it was exactly like the S-duality that we know,
Yeah.
like electromagnetic.
Yes. No, but for 2, 3 and 4, what happens is, there is S and S prime, so P and S prime generate gamma 1 alpha. So S prime was S, P, S, M. So we have a subgroup generated by S prime and P that belong to the modular group. But there was still S. The full duality group is...
And tau still went to minus 1 over tau.
Yeah, minus 1 alpha tau.
So that's what I'm saying. So tau going to minus 1 over alpha tau is also, you're identifying that also as electromagnetic.
Yeah. So the electromagnetic duality group is bigger than this.
Bigger than that. Okay.
So
So it's some kind of modified. It's some kind of modified electromagnetic duality in which.
No, it's a traditional electromagnetic duality.
Oh.
It's just that, see, nobody tells you the electromagnetic duality group should be SS2.
Okay.
That's a misconception that people have from doing SU2 theories. For higher rank, it's really not true.
And your J function formula had this invariance as well.
Yes.
Had more than SL2.
Yes. Okay, good. So now let's see what happens to n greater than 0. So for n equals 0, it's just a nice modular form. And greater than 0, we find a sort of recursive structure. Going the lower g's, you see that SGN is almost modular, but there's the anomalous transformation, which depends on all m lower than n. It should be m less than n. And so these are sort of almost modular forms of gamma alpha, and this gives you the weight. But there's an anomaly. So the question is, how do you quantify that anomaly? Yeah.
What is little n again? Just
Little n is what appeared in the semi-classical expansion of the dual equations. The successive terms at higher and higher a.
And just to understand exactly when we get there, we know how the UV S-duality acts on the masses.
Yes. I think so, yeah.
Okay. And that will play a role in this.
But here, in this example, it doesn't play out because it's the nth Casimir is here. This is even invariant up to a sign. Not a sign, but
is this roughly the nth instanton center?
No. So this is a semi-classical expansion. Inside this, each GN will have a. I'll show you an example. We'll have an internal expansion. I'll show you an example. Let's go to the general story first. So here we have an anomaly. And the question is, how do you quantify the anomaly? And we claim that the anomaly comes because, apart from modular forms, I have the second Eisenstein series present. There's a common trick that people use in various contexts, topological strings as well, and also other base theories done the same trick. So it's because under a sort of S transformation, this is just minus 1 by tau 1, E2 transforms like this. There's an anomalous contribution to the modular transformation of E2. And we can suitably modify this to define an E2 for every gamma 1 alpha by combining this with modular forms of gamma 1 alpha such that it transforms like this with the right root alpha. It uses some doubling formulae and so on, doesn't matter. And now our proposal or our ansatz is that Gn is a polynomial in modular forms and E2. And the anomaly should come only from the presence of E2. Which means if I do an S-duality, everything should transform as they should, except E2 is shifted. Okay, and the shift can be written in terms of a first derivative plus higher order corrections. And you compare this equation with this equation, and we find such a equation. Okay? We find a sort of modular anomaly equation for the G coefficients that completely fixes the anomalous behavior of G. And the modular spaces can be fixed, by comparing with the known instance expansion that we do as a power series using locus. Okay?
How do you know this proposal is correct?
We just do it constructively and show that it actually works.
Which means you.
So let me give you an example and hopefully it will work.
might be a conceptual issue.
Okay, so let's take SU2. So let's take SU4, which had these two coupling constants, and only one of them appears here. If you put in the numbers, this is what you find. And what are the GNs? So you see, GNs are like this. So you have a mass Casimir times some few expansions. So this is actual instanton contributions. G1 will have two mass combinations. Each of them will have their own few expansions. Okay.
And this is through localization.
Localization, and here I've sort of expressed everything in terms of already and I used the Q0 was tau1 map and written everything in terms of Q1 because the modular structure is only visible in terms of this renormalized coupling constants.
Q1 is a Q form from tau1.
Exactly, e to the 2 by tau1. Exactly. So now, if what we said is correct, G0 should be a modular form of gamma 1 2 with weight 2 and as parity 1. And if you look at the table, well, there's only one guy. It has the following two expansion. Comparing with the earlier expression, G0 is fixed completely. Okay, so it depends on the fact that there's a finite number of basis elements and the fact that we know the first few terms of the expansion. These two things fix G0 completely. What about the high G's? Again, if you go through this analysis earlier, you'll find that this is the modular anomaly equation. Okay? So G0 is known. I can just solve for G0 here. I put that in here, integrate with respect to E2, and I find that it's this plus the modular piece. Okay? Again, you list what are the basis elements of the modular forms of the given weight and S parity. You find that there's only one. So this is the full sort of instanton with some dancing. Because when we get modular forms, we do the same analysis of the period matrix. There is S of G's that appear for the period matrix. What we find is that you find tau1 and tau k both appear. So essentially, it's a ratio of modular form of 1, which should be alpha 1 and alpha k. So it should be two different modular forms. The ratios will give you the leading terms of the period matrix expansion. Again, there's a slightly more subtle structure here. Instead of finding a single anomaly equation, we find coupled modular anomaly equations. So you have some coupled equations, and again it's complicated, but let me just give an example and hopefully you can share. So for SU4 you had two coupling constants in that. Again, mass corrections don't change the matrix structure. The raw data looks like this. I have some. Each tau tilde has some expansion. This is the massless guy. This is the massively formed expansion, and they all have some Q0 expansion. Now, from this is not apparent because any modular structure, because some rational functions. The claim is that if you just go through what I just said, you can fix the leading coefficients completely in terms of ratios of modular forms. And the same is true in the higher case. In the higher case, we have some coupled equations. You can solve them. You can show they're always integrable. The coupled equations. You can solve them, and again, I'm just flashing the slides. So we can go up to G4 or G5 easily. I think I'm done. Here's some open questions too. I hope the basic idea is clear. So there are many questions one can do from here on. We just focus on the simplest calculable quantities. Not even the full prepotential. We just calculated the period, the dual periods, and the omega matrix, period matrix. We show that the special vacuum, they show this quasi-modular behavior. And we can ask if I take trace phi to the n, does it show modular behavior? In massless case, the answer is yes. The massless case, we just try to understand that right now. So this is something that was asked earlier. Can we do this mass deformation business for the non-arithmetic cases? So we need sort of the analogs of the Eisenstein series and automatic forms.
Actually, the thing is that all these guys are algebraic. So it's, I would say, for example, things like square root t, those will not be in SL2Z, but they will be integers in SL2, say, Z root t.
I see.
And more generally, you could have some algebraic number.
Okay.
So solution to some polynomial thing. You adjoin that to the two rationals, find the ring of integers. So those are lattices. I mean, those are slightly more complicated lattices, but the arithmetic technology still goes.
Both, I see. So if you can.
So these non-arithmetics are arithmetic in some higher lattice.
I understand. So if you can understand that and apply this, I don't think this. I mean, there's no reason why this should not work.
Yeah, so for SL2, so this SL2Z is a lattice in SL2R. So for quadratic integers, it will be SL2R cross SL2R. And there you can push through a lot of the...
Yeah, so we are stuck somewhere, so we have some mass gap to encounter, so to cross. So if you can learn the technology, then yes, in principle, the same sort of structure should hold even there. So is a question.
There's going to be one difficulty because here you have a lattice proper that is going to sit as a subgroup of a lattice.
Oh, I see.
So then yeah, there might be technical. There is some. These are called Hilbert modulars. I mean, if you want to Hilbert modular forms.
Wait, something to Google.
Yes.
Okay, so the next point is that it would be nice to see if we can extract some physics out of all this, because we seem to have only some expansion, at least in some special locus of the Coulomb branch. So you know, these J invariants have, as I said, more expansions near the cusps. So we're hoping that we can extract some physics out of this point. And lastly, of course, we should move it to the special locus to see if you can say something more general about the full moduli space, some high rank theta functions, or something like that. I'm done. Thank you.
ICTS, questions from ICTS? Somebody might switching to visual.
So they are.
Is ICTS that?
They were connected to begin with.
Yeah.
Okay, fine. Okay. TI.
Let me just try to understand. So there's something very basic I didn't understand, which is just by writing the Seiberg-Witten curve down, let's say we weren't so interested in the action of S-duality and so on, but we just wanted to understand the physics of the theory, where monopoles condense, so on and so forth, what are the gauge couplings and so on. Now, can't you extract all of that just from the Seiberg-Witten curve in the first place?
Yes. See, but this is not the U plane that I talked about last week. Here we have an H plane. See, this conformal theories have a new parameter. We have the U case, now we have this H. And all we're talking about is what happens.
The physics of that?
Yeah.
Okay, I see.
So in some sense, we have sort of.
No, but just to repeat that. From the Seiberg-Witten curve,
Yes.
one can, in principle, maybe hard in practice, find the formulas for all the U1 gauge couplings.
Yeah.
In terms of the parameters of the curve.
In terms of by calculating the P integers.
By calculating. And you knew what the parameters of the curve were in terms of the Bayer coupling. That was your formula for H in terms of Q naught, right?
Yeah.
Okay, so in principle, the formulas for the U1 couplings in terms of the UV data is there in the Seiberg-Witten curve.
Yes.
Now, one of the main formulas in your talk seemed to be precisely this, that is, relating the U1 gauge couplings to the Bayer couplings.
Yeah, but if you just do P integers, and if you just calculate the Bayer matrix from the Locus formalism, it's not clear if there's any structure. So in terms of Q naught, the modular structure is invisible.
Okay.
Even if you do a series expansion.
But actually, just one second, if you don't mind. So suppose you took that formula that you had many times, that formula with Q naught is equal to something in terms of J's of towns.
Yes.
Okay? That might have been hard to directly derive from the Seiberg-Witten curve, but certainly should we be able to at least test?
Yes.
Give that this formula is consistent with the Seiberg-Witten curve. Because this formula I can read as giving me all my U1 couplings as a function of Q naught.
Yes.
Once I have all my U1 couplings, I have A and A dual as a function of U naught. And I should be able to check whether that is what comes out of the Seiberg.
Yeah, but you see, these are very specific couplings that multiply specific matrix structures.
So those are the only ones that arise in your...
Yeah, but if you don't know the matrix structure that is of relevance to start with. Yeah, but I agree what you say. You can probably check what you just said. Yes, you can. Yeah. If you can isolate those matrix structures, yes.
So the difficulty was just technical. Going from the Seiberg-Witten curve to this formula, even though all the information was there, to this formula is a horrendously technical job.
Yes.
That's the... But by thinking about S-duality and so on, you were able to fix this formula. Is that a fair?
Yes.
I mean,
that's sort of so. Okay, let me just try to make sure. I'm just trying to
Maybe
understand.
it will be useful point of view if we go away from the special locus instead. Is that point?
Yeah, I'm just trying to understand exactly. Yeah.
No, that's right. I was also trying to understand. So let me try to understand. So here what happened was you did a very beautiful analysis, and at some point you found the structure fitted various modular invariants and so on, and you could write it very nicely, right? But in some sense, it's you did a localization calculation which gave you some terms, and then you guessed the modular transformation properties, and you sort of completed it and so on, and you got the full instanton corrected answer, right? But in some sense, all of that is already there in the cyber written.
I would disagree slightly. In principle, yes. In principle, yes. Because you see, this is what is not obvious. Usually, what you get is this. The sigmas are some. You have some matrix structures and some sigmas as coefficients.
But it will come out of the cyber written curve that it has this particular form.
Without S-duality. How?
Because I thought cyber gave you the full power.
I want an exact form. You are saying, suppose you know the exact period matrix.
Yes, suppose you calculate any integral that you want to get.
Exactly. Not as a real special function, not as an expansion.
Yeah, suppose for a moment that you were infinitely powerful, you were Mathematica prime, and then you would find the integral that had this matrix structure and be able to derive all of these.
Yes, but in practice, unfortunately, what happens is, just for clarify, what you have is a series expansion. That's the problem.
But that's a question of, it's not some, that's a question of just computing period integrals of some hyperelliptic surface, right?
Yeah.
How hard can that, it's not doing some field theory instant.
To be fair, in the Zian invariant case, I think it's possible to do it exactly in terms of hypertonic functions. In the Zian invariant, in the simple case of the XDN that we work with here, I think you can do the period integrals exactly in terms of. I think our collaborators might have done it in some earlier paper as well.
And just to point to that, right? Just take y square equal to x minus a1, x minus a, and look at the symmetries the group it generates. There are questions about, in a different context, when this is arithmetic, when this is non-arithmetic. So Hecke has done some very serious work just a couple of years back. So it's not clear.
It's not, it's a hard.
These are general hyperelliptic surfaces.
For us, the hard part initially was to find the right basis in which the diagonal.
I understand. It's very beautiful. But I just want to understand also. I keep going. Please. Okay. Yeah. So in the case that you were saying that you could actually do the period integrals, then can you from that answer recover what you have, or check the consistency of?
I think I should be able to. Yes, I think you're right. Yes, we should be able to.
Okay. Great. Now the next question is like, let's say that for a simple case. Let's say the first case where there are two U1s. SU4. Yeah. In that case, again, the cyber written curve has everything. So, shouldn't one be able to go away from the special point just constructively, or just the period integrals are too hard?
So, let me just say that the first time that this modular anomalies are encountered, it was by Minahan, Nemachansky, and Warner. With the SU2, I think, n equals to star, they did exactly what you said. They used the curve to derive the model anomaly equations. And they computed this F, the prepotential to see the paper, the pages and pages of them.
In a series expansion.
Yeah. But with coefficients being modular forms of S and 2Z. Because for n equals to star, it's really S and 2Z.
I see.
So they could use as E2, E4, E6 and just do it. So indeed, you can do it with the curve.
I see. Yeah. And then the element that also was thrown in was this question of how the genuine S-duality group of the UV theory it manifests itself in the IR.
There's no UV IR is conformed, but yes, in terms of these effective parameters, yes, exactly.
So once you're a Coulomb branch, there is an IR theory. Okay, so and that was really very interesting. So very complicated.
Yes.
Very complicated relationship we might not have expected. You might have naively thought there's no running, so just
exactly. So in fact, for n equals to star, that's exactly what happens. Tau 0 is tau, and there's no mystery.
Yeah. And one of the consistency things there was that it must be that the UV duality group always is embeddable inside this SP. And that you can just check. That statement is true, that's obvious. Does one know the UV duality?
If Q0 is a parameter in the curve, which it is, then it's just acting on the cycles of the curve.
Okay.
The H that appeared was a function of Q0.
Okay.
So you would definitely say that yes.
It was obvious.
Yeah.
I see.
But physically, these finite, as you said, the theory is conformally invariant, and so the corrections you're getting are like some finite corrections.
Yeah.
And are they, so in the ultraviolet, your theory is conformally invariant.
Well, you give this Coulomb branch type, so there's a scaling problem.
Yeah.
Exactly.
Now I'm coming to that exactly. In the ultraviolet, the theory is conformally invariant, but then you're out in the Coulomb branch.
Exactly.
Now what that gives is masses to various fields. So are these like threshold corrections, which result in a final low energy coupling, which is therefore complicated?
Yes, I think so.
You're computing.
Yeah, I think Ashok mentioned this well when I think Madhu was giving this talk. Yeah, I think that's correct. Yeah.
That's what it is, that you computed all the threshold corrections.
Sort of resum them into this.
Resum them into this beautiful expression.
Yeah, and you might have thought, and as you said, in some cases, sometimes you just do a dumb matching, right?
Yes.
Yeah.
Running, and nothing's running here. So
More running, less running, and then you will do it.
In the
yeah.
sort of
And here nothing runs, you might have thought this should be that. But it's more complicated.